This video gives you a complete example of how to solve Laplace's equation on an interesting domain using the solution of Laplace's equation on some other domain that's a little easier to work with. This has a specific application, that being finding the voltage or electrical potential, because the electrostatic electrical potential is a solution to Laplace's equation, or otherwise a harmonic function. And the problem we're going to work on is the potential inside a cylinder with two electrodes. Mathematically, the problem is formulated like this. You want to find the electrical potential, or the voltage, on a disk of radius 1, in which there's a top boundary, that's one electrode, and that's kept at a low voltage of 1 volt, and the bottom is at a higher voltage, 1 volt. Of course, in reality, it might be larger. And there's no connection between the two, so at each of these points here, there's no connection, which is to say that the electrodes with 0 volts and the electrode with 1 volt they're not touching at that particular point. Now, this sort of thing actually is a real device that's actually used. Roughly speaking, it kind of looks like this. So the red wire is the plus voltage, the black wire is the 0 voltage. And there's some insulator in between. You can see there's no connection in between, and similarly on the other side. Typically, this is used to steer an electron beam. So you have a beam of electrons coming down this pathway here, and they're repelled by the negative, the black wire, and attracted to the red wire, the positive wire. And so you can steer the electron beam one way or the other by changing the voltage. This is actually something that you'll see in old cathode ray tube displays. And so, in particular, here is an old oscilloscope that has an electrostatically steered display. The display is in the front there. And way in the back, the electrons are generated and they're fired forwards, and they strike the screen. Right where I've circled in red here is where this particular equation that we're going to solve lives. There's some electrodes there that do the beam steering. So that's a very practical, very realistic application. And so if we can solve this, we can have an idea of how such a device might function, and perhaps use this information to help design it. Okay, so mathematically what we're after is we want to solve Laplace's equation on this disk. It's a Dirichlet problem. So this is a Dirichlet problem because we've specified the boundary values. Dirichlet problem. And the point is that the voltage, Vxx plus Vyy, or the second partial of the voltage with respect to x and y, is 0 for x squared plus y squared less than 1. That's inside the disk. Inside the disk, that's what's going on. And the voltage is equal to 0 if x squared plus y squared is equal to 1 and y is strictly positive, and it's equal to 1 if, again, you're on that boundary circle and y is negative. And when y is equal to 0 and you're on the boundary circle, we have no information. Okay, so that's the setup. That's the problem we want to solve. And if you're comfortable with polar coordinates and differential equations, you can probably rewrite this equation and go to town solving it. That's certainly workable. But let's instead make use of a conformal mapping to simplify this. Really what we want to do is we want this conformal mapping to take the point z equals 1 right here and send it off to one spot and send it off to either 0 to or infinity, and move the other point, the negative one, to the other point, either infinity or 0. So, tactic, conformal mapping. And the picture that we're going to try to do is we're going to take real part of z, imaginary part of z. We'll call this x and we'll call this y. And we're going to send z's to w's. This is the real part of w. We'll call it u. The imaginary part of w, we'll call it v. And what we want to do is we want to take these 2 points on the unit circle, and we want to map them. We want to map the the point 1. We want to map that somewhere. Let's put it on the origin. And let's map it so that this whole region here, I'll mark it in heavy black because this is the negative terminal or the 0 volts terminal. We're going to map that whole thing onto here. On the other hand, the positive terminal, this guy here, if you look at how this will go, it'll be off in here. It'll be the negative real axis in the image. Everything on the interior will end up in the upper half plane. And what about this poor point here? This poor point here gets mapped to point at infinity. The reason for doing this particular conformal mapping is because it's much easier to solve Laplace's equation in the W space, in the upper half plane, under these boundary conditions that I've given you. It's much easier to solve it there and then pull the solution back to the disk. Okay, so that's the plan. So we're going to need a conformal mapping that does that. Well, if you look at it, the conformal mapping in question needs to have a 0 when z is equal to 1, and needs to have a pole at z equals -1. And we also want it so that it'll be the upper half plane being the image. So the conformal mapping question is a Mobius transformation. W is equal to f of z. I times, well, I want a 0 at z equals 1, and I want a pole at z equals -1. So that transformation that I've written there will affect this conformal mapping. You'll notice that because of the video that I have on where is a Mobius transformation conformal, we realize it's actually conformal everywhere, with the possible exception at the pole, at the z equals -1. Even though, actually, if we think about it in terms of the Riemann sphere, that's fine too. This is the right transformation. Okay, so now we need to solve Laplace's equation on the W space. Let's do it. So let's solve it on the upper half plane. W space. And the picture in question is this picture here, so let's copy that picture over. And we can write it out formulaically to say that we want our solution, our voltage, v is a function of u and v. We want it to be equal to 0 for v equals 0, u greater than 0. We want it equal to 1 for v equals 1. Oops, v equals 0, u less than 0. Okay, that's what we want. And if we think about the functions that might do this, one function actually kind of jumps to mind. We're really kind of imagining the level curves of this function. Let me erase these gray guys and draw some level curves. We really want the level curves to be kind of like this, emanating from this origin, and we want the voltage to increase because it needs to be 0 on the positive real axis and needs to be 1 on the negative real axis. Well, that looks pretty much like an angle function. What function that we know of will do that? Well, in fact, a little bit of moment's thought suggests that we're really dealing with a logarithm. So if I say capital W of little w is equal to 1 over pi times the logarithm of w, and this is the principal branch, so the argument is between minus pi and pi. If I do that, then this is 1 over pi ln length of w plus 1 over pi times I times the argument of w. And the argument of w ranges between minus pi and pi. Of course, what that means is it's 0 along the positive real axis and it's pi along the negative real axis. So in the upper half plane, the argument of w is between 0 and pi. So this whole ratio, the imaginary part, is between 0 and 1. And notice it's right what we wanted. This is an analytic function, except at the origin, which the origin we're kind of excluding anyway. So the real and imaginary parts are harmonic. So capital W is analytic. So imaginary part is harmonic. The imaginary part satisfies the boundary conditions so, and this is by the existence and the uniqueness of solutions to Laplace's equation. So V of U and V equaling 1 over pi. The argument of W, W is U plus IV, is solution we seek. Of course, we can rewrite this. This is the arctangent of V over U under the appropriate branch choice for the arctangent. Great. So that means we've solved Laplace's equation in this domain in the upper half plane, and it looks pretty much like the way I've drawn it with its level curves. All right, so now what we want to do is now we want to transform it back to the disk using our Mobius transformation. So let's pick up that Mobius transformation. And let's go to the next page. So now using our Mobius transformation. Okay. Let's rewrite this Mobius transformation using x and y coordinates and pick out the real and imaginary components, i.e. the x and the y's. Okay, so this is 1 minus x minus iy, and this is 1 plus x plus iy. We want to rationalize this equation. So multiply by the conjugate. So there's a lot of terms, but there's really not really a problem, I guess. So this is 1 plus x minus iy minus x squared minus x times minus iy, x iy, and then minus iy minus I xy, and 2 minuses is a plus, but 1 I squared is a minus y squared, so that's the numerator, and the denominator. And plus x squared and minus ixy and plus iy and a plus ixy and a plus y squared. Okay. I can see some cancellations right away. So I have a cancellation here and here. I have a cancellation here. And let's regroup accordingly. One. Oops, more cancellations actually. Minus 2iy minus x squared minus y squared. And the denominator is easily found. It's 2x squared y squared. Okay. Successfully gotten all the real and imaginary parts stuffed into the numerator. So I can regroup this entirely in terms of real and imaginary parts. So I have a 2y as my real part. And as my imaginary part, I have a 1 minus x squared minus y squared over okay, great. Now, remembering what these are, this is u and this is v. I will now want to make use of this information to rewrite my v. So what was my v? Here's my v. V of u and v was 1 over pi arctangent V over U. And so let's make sure I got that right. Yes, indeed, 1 over pi arctan V over U. Good. So rewriting this in terms of x's is now not a problem. So the v is 1 minus x squared minus y squared. The I is not part of the v. And you'll notice the denominator is the same on both of these guys, the u's and the v's, so they'll cancel out. And I'm just left with this expression. Okay, and so now this is actually the solution that we sought from the outset. You can check it if you notice that we dial in an x squared plus y squared equals 1. The numerator is 0. Arctangent is ambiguous there and really depends on the sign of the y. And indeed, that's what we wanted. Okay, now, at this point, we're done. It's good to take a step back and look at it from a visualization standpoint. So let's do that now. What we have here is this on the left side, right here, left top frame. That's the solution we found. So this is that expression for v in terms of x and y. On the top right frame is the v in terms of u and v. Here's the u coordinate and here's the v coordinate. You'll notice, indeed, just as I said, it's really the angle that we're measuring here. That's a harmonic function. Now, to kind of visualize what's going on in terms of the Mobius transformations, I've drawn these same two plots on the Riemann sphere. The Riemann sphere is covered entirely in the right side in the W domain, and there it is, and you can see the Riemann sphere in that case. That's actually very much just an angle. And if I look at it, I'm looking at the point at infinity right at the top here. If I flip it over and look at, there's the origin, and you'll notice, and since we're looking at the bottom, this is going around, it looks like I'm going around clockwise, but I'm actually going around counterclockwise. So there's the positive u-axis right here, and as I move around this direction, I'm moving around this direction here. And of course, it's mirrored on the other side. The whole thing is the component of an analytic function. Now, this point and this point here that you see, they're the images of the 0 and infinity through the Mobius transformation. That brings us over to here, where we've pulled back our harmonic function onto the Riemann sphere in the z coordinates, i.e. the x and y coordinates. Now, that's only valid within the unit disk. So outside the unit disk, there's nothing to be said. That's why it's all blue here. And again, I'm looking at the bottom, so everything's flipped. There's the origin. So the origin here, where did that get mapped? Well, the origin wasn't a particularly special point in our Mobius transformation, and it happened to get mapped down here. Because really the special points were the point 1 and minus 1. Those guys ended up as the 0 and the point at infinity. So this is the point 1, and this is the point minus 1. The point 1 got mapped to 0, and the point minus 1 got mapped to the top of this guy, to the point at infinity. And indeed, you can kind of see that this picture here is what's going on over here. This picture is what's going on the bottom over here. And so that's in fact how this transformation works. So we really sort of grabbed this angle formulation here and stuffed it back onto here. And this is really what the voltage looks like. And indeed, this kind of solution explains how an electron beam does get steered by this kind of setup with an electrode. If I have a positive electrode here and a negative one here, if the electron beam starts out in the middle, the electrons will get attracted, kind of pulled over to the electrode, the positive electrode, and they'll kind of get pulled over and the beam will spread out a little bit. And so actually typically there's a series of other focusing stages in a typical cathode ray tube to compensate for that effect. So you have the beam steering and you have some beam focusing electrodes as well, and they all kind of fit together to try to keep the electron beam together so that it scans a nice narrow point across the screen. So in summary, what we've done is we've taken a trip through this problem where we started out asking for the solution of Laplace's equation on this disk. We've got some Dirichlet boundary conditions. We've transformed this into a domain that was a little bit easier to work with, and one in which we could actually guess the solution to the Laplace's equation, i.e. realizing that it was the imaginary part of an analytic function we already knew. And then we just pull it back. We pull that solution back using the conformal mapping, and the conformal mapping in question happened to be a Mobius transformation, so we understood that very well. This is kind of the power of using these conformal mappings. On the other hand, you can see that there's a disadvantage. The disadvantage is we did a lot of work by inspection and a lot of work by, hey, I happen to know something. So using these kind of complex tools to solve Laplace's equation in various settings is something that requires a bit of finesse and requires a bit of skill. That's in part explains why solutions of Laplace's equation now are typically done numerically with a computer. You don't need that finesse if you have lots of muscle.